Good morning, everybody. I think we can start with our session for today. And the first speaker is Paolo Bignardi from University of Pavia, who is testing the stencil. And he will be speaking about the wave equation, continuous and coercive variational formulation in space-time. And we didn't have the intriguing subtitle, so I leave the floor to you to explain the intriguing subtitle.
Yeah, sure, of course. Thank you. Sure, yes, of course. Thank you all for being here. Yes, the subtitle is a bit facetious, and by the end of the talk, hopefully, it will be clear what I mean. Okay, so this is a recent work I've been doing with Andrea Moiola. And yeah, it's about space-time formulation for the wave equation. So we're interested in the wave equation, time domain wave equation with impedance boundary condition. Why space-time? Well, it's we thought it was a nice framework for domain decomposition, not just the domain decomposition in the sense that we decompose the spatial domain, but also the whole space-time cylinder. So it gives more flexibility. Also, it was intriguing. Just for one intriguing part was high-degree polynomials or high-order elements in general. And a very interesting aspect is adaptivity. In a sense, again, not just in space, but we would like to refine the mesh locally in space, but only for some times. So we can leave a coarse mesh for some specific times, and some other times we want a coarse mesh, fine mesh. So this is something that with space-time we can straightforward, we can do quite straightforwardly. Okay, and then some parallel implementation because why not? Also, no. Okay, so this is now. Let's look at what has been done so far. Okay, let me stress this point. We're interested in conforming discretization. So we are not interested in any DG methods, Treft DG, nothing like that. We want conforming, just a requirement that we imposed. A formulation was proposed by Steinbach and Zank in 2020. Basically, they proved that the wave equation, they proved well-posedness of a discretized problem for the wave equation in space-time using piecewise linear functions in both space and time. Okay, so now this is an intriguing result, but it's for Dirichlet boundary conditions, and it's unclear how to generalize to the proof of the well-posedness to higher order functions. There are some numerical tests that seem to suggest that this is possible, but the proof is unclear, and it is unclear how to generalize the proof from the linear case to higher order. Another starting point was the Helmholtz formulation, coercive formulation for Helmholtz, proposed by Moiola and Spence in 2014. This formulation is based on Morawetz multipliers and a strange non-standard space and a norm which is stronger than the usual norm in H1. But with respect to this non-standard space and with respect to this norm, they prove coercivity of a bilinear form, so they fall back on a Milgram setting. Okay, so the main point is Morawetz multipliers, and we'll talk about them later. Okay, brief overview of what we're going to see in this presentation. So we look at an abstract framework for Morawetz identities, which allows us to define a formulation for any generic problem based on Morawetz identities. Then we look at the problem that we're interested in, the wave equation. Then we'll talk about norm and space definition. In this case as well, the norm and the space is not is not a standard one. Then the main result, which is coercivity of the bilinear form. We'll talk about well-posedness of discretization and causal-optimality, of course, and give some example of finite elements and some numerical tests. Okay, so so the main point, the main point I want you to take home from this presentation is that this is just we can just define a bilinear form with prove coercivity in space-time, and effectively this is just Lux Milgram. So it's like first course of functional analysis. Okay, so it's quite straightforward. So let's consider this abstract problem. Okay, we have a PDE and some boundary conditions, and we assume we have this operator Z. Okay, I'm not being specific about the regularity of those functions. So I'm just being a bit sloppy in this case. But let's consider this as collinear form. The problem can be even complex valued. It's not can be as general as we want. And we define this as collinear form. That has nothing to do with the problem, but is the Morawetz is basically the starting point of the Morawetz identity. Okay, so we consider this integral, and the Morawetz identity comes from writing this integral by using integration by parts and doing some manipulations which differ from a case by case. We assume that we can split this basically the Morawetz identity in two parts, X and G, which are in a sense prescribed. Okay, so what we assume is that G reduces to a linear form that depends on the boundary condition data whenever the boundary conditions are met. Okay, so inside of G only stuff related to boundary conditions has to be put into, and everything else gets dumped inside of X. Okay. Also, this identity holds, which is nice because we will need it to give to talk about coercivity. Okay. Okay. So let's define the actual problem for the actual bilinear form for the abstract problem that we considered. Okay. So let A be strictly positive, and this is the bilinear form of our problem. Okay. This the abstract problem. Okay. I want to convince you that this is the right bilinear form. Of course, if we take U that satisfy the PDE and the boundary conditions, then using this identity in red, we can say that B is equal to this thing here. Okay, using this identity here. Okay, just substitute. Now, since LU is equal to F, we can substitute into here and into here, and using the fact that the boundary conditions are met and the assumption that we made on G, we can write this. We can say that B is equal to this thing here. And if we define the linear form in this way, then in a sense, what we have created is a formulation for this abstract problem. Of course, we do not know anything about well-posedness at this point because we did not prove coercivity at all. So, indeed, for coercivity, what we need to check is should be the real part of BUU, which by doing some computation is equal to this thing here. So when we want to check for coercivity, we just need to lower bound this. So it's just a convenient. It's just convenient to have this formula here. Okay, so at this point I want to move on to the actual problem, the wave equation problem. So we have the second order time domain wave equation, impedance boundary conditions, and some initial data. Okay, we need to make some assumptions. We say that L is the diameter of the space domain, and we need to assume that the space domain is also star-shaped with respect to a ball, not a point, but a ball. This is a technical requirement, but it is what we need. The other thing is that we need to assume that the initial datum u0 as null mean. Okay. In this case as well, I'm not being very specific about the regularity of f, g, u0 and u1, but hopefully it will be clear later. Okay. Okay, let's talk about Morawetz multipliers. Now, they were first introduced by Morawetz in 61, and then were used by her and many others in 75 and later. They're a very powerful tool. They're used also instead of the virial theorem to prove energy estimates for PDEs. It's a really powerful tool. Now, the idea is the same as the one that we saw earlier. So we should, sorry, the idea for Morawetz identities and for Morawetz multiplier is to compute this integral here. Okay, and when we do it for u equal to v, we can get an estimate of the energy of the PDE. In this case, we are not interested in energy of the PDE. We are just looking for a formulation for our problem. Okay, so in our case, we need to define the operator z, which was just a general operator, and this is what is our definition. This term is usually the one that comes out from Morawetz's papers. We also had this because it's a bit convoluted, but so I'm not going to spend too much time talking about it. And we have some parameters, xi, beta, t star, and nu, which we need to find conditions for coercivity. We need to define them for coercivity. So, using our abstract framework, we can define the bilinear form and the linear form. We just need to define x and g. So at this point, we need to compute x and g by just integration by parts and some manipulation. So I'm just going to show them here and never again. So this is x, this is g. They're pretty ugly, of course. There are a lot of boundary terms, but this is actually what we need. I want to stress one thing about g. Notice that, as I mentioned earlier, g only contains stuff that is related to the boundary condition. Okay, so if whenever the boundary conditions are met, so also initial condition has to be considered as boundary condition in this case. Ut is known, the gradient of u is known, ut is the same thing, and this thing here is known due to the impedance boundary conditions. Okay, so whenever the boundary conditions are met, this whole thing is only depending on v. Okay. Okay. So of course, to prove coercivity and to talk about coercivity at all, we should talk about spaces and norms. The first thing we do is we introduce a norm because it's the simplest thing to do, and then we will get the space as the closure of a smooth function with respect to this norm. Okay. Now, the norm that we need is the simplest norm in a sense that yields continuity of both b and f. Okay. So this is the definition of the norm. There are a lot of terms, derivative and gradient in the space-time domain and on the boundaries, space boundary, and on the starting time and the last time. Okay. As I said, we define the space as the closure of smooth functions with respect to this norm. And the standard Lax Milgram formulation is just what we'll extend. Okay, so this is just very simple. Okay, so the main result is this one, which is coercivity. Okay, again, if we choose the coefficient of the Morawetz multiplier in a suitable way, then for a smooth function we can prove the coercivity condition. Okay. Of course, clearly, since we define the space as the closure of smooth function, this also holds for all the functions inside of the space V. Moreover, I want to point out that the coercivity constant depends on the star-shapedness of the domain. Okay, the more star-shaped the domain, the better. And also depends on this A, which is a least square term that appeared in the definition of the norm. And in a sense, we would like these two coefficients to be as similar as possible. Okay, so in order to balance them out. Okay, so of course this is as I mentioned, it's a very simple Lax-Milgram setting. So at this point, if we choose as in Laplace equation, let's say that, as soon as a discretization is conforming, well-posedness is guaranteed. Okay, so it's in this sense, and in the sense that we prove coercivity, we can in a sense say that the wave equation in space-time can be considered as an elliptic equation, but it's kind of stretched, but so it's fine. And the other thing, of course, is quasi-optimality, because again, if we have a conforming discretization, then we can use Selle's lemma and get quasi-optimality. Okay, so the big question mark that still remain is the space. Now, the space that we defined was V. Let's consider for a moment this space H, which is just the space of all the functions in L2 on the space-time cylinder, such that the norm is finite and the initial mean is null. Okay. Now, clearly, this space H is bigger than the space V that we defined. Okay. But we do not know whether V is equal to H. We don't know the opposite inclusion. Okay. So, in other words, we are interested in knowing if smooth functions are dense in this space H. If they are, then we can give a better characterization of this space. But so far, no luck. Okay. So. We would like, we're working on this right now, so it seems it's not trivial, so yeah, I'm not going to say anything more. Okay, so since the norm contains some traces and some boundary, also some boundary terms, some kind of trace regularity is required in some way. One important thing for application, for doing computation actually, is that V contains the piecewise polynomials with C1 regularity. It's C1 regularity, it's asking a lot, but at least we have something. So let's consider a simple case. This is if we consider the space of piecewise polynomial with C1 regularity, we can take tensor product in each component of C1 elements, and this is what we do in this simple example using Hermite polynomials of degree 3. I think yes, 3. And if we do it for this simple case, we have one-dimensional space domain, and we use one-dimensional Hermite polynomials over a uniform mesh, and we do the same thing for the time component. Doing some tests, this is what we get. Okay, this is a homogeneous boundary conditions. So everything impedance is homogeneous and homogeneous initial conditions. But of course the problem is non homogeneous, because otherwise we get no solution. And this is the convergence rates that we obtain. Okay, they should be optimal. Okay, so it's 4 for L2, 3 for SH1, and we also show the L2 residual, because it's in a sense related to the norm. To the inside of the norm there's also basically the L2 residual. So inside of the norm of the space there is also this term here. let's consider a more interesting problem, a more physical problem, say, which is the problem of a single wave packet traveling through time. Okay, so this is the wave profile, the initial wave profile. They're just two Gaussians summed together, one is flipped. And this wave propagates with constant speed towards the right. Okay, this is a space-time plot. Okay, so the waves propagate in this direction, and as soon as it hits the boundaries of the domain, the wave is reflected, and due to impedance boundary conditions, not all of it is reflected. Some of it is absorbed, and of course the rest is reflected in the other direction. Okay, so in this very interesting case, again we get convergence errors, just so it's what we expected, and yes, of course a pre-asymptotic phase, but okay, so next steps are looking at star-shaped obstacles, so the scattering problem. In that case, still we need to assume that the scatterer is star-shaped with respect to the ball. Okay, I think that should be a requirement, but I'm not 100% sure. So basically, we can. It shouldn't be difficult to extend to this case. Also, variable coefficient equation. So non-constant wave speed. This would mean that we need to modify the Morawetz multiplier, because the Morawetz multiplier should reflect the characteristic lines of the problem. And in our case, in the constant case, characteristic lines are just straight lines. In the case of variable coefficient equation, they are no longer straight lines. But if we modify the multiplier to take into account this fact, then I think it's, in a way, yeah, I think it should be straightforward. Mark my words, hopefully. And at last, we would like to give a characterization of the space, just to be, just for curiosity, actually. And since we are going through the trouble of developing space-time methods, we should use fast solvers, because of course the problem, as you can imagine, is quite large. And so as we increase the dimension, it becomes a challenge to solve the linear system. So this is all. Thank you. And
okay, is there any question from the audience? Please go.
Thank you, Paolo. Do you think that the norm that you have chosen to prove coercivity is the minimal norm to prove coercivity, or you can, I don't know, maybe simplify some term using some estimate?
Okay, so let me get the norm. It is the minimum norm that we need, because if we look at, okay, I have to show them again. Sorry. If you look at x and g, we need a norm that contains all the terms that also are in x and g. Okay. Otherwise, we do not even have continuity. Okay.
So there is no way to simplify it.
Yes, exactly. Yeah.
Okay. Thank you.
Okay. Is there any other question from the audience?
Thank you, Paolo. I don't understand whether you use the zeroing condition on the initial.
Okay, yes. It's just a condition to guarantee that to guarantee that this norm, this is actually a norm, because in this norm there is no function term. There is no say zero order term. So we need it to for that reason. Yeah.
Actually, I have a couple of curiosities. So, all of this is because you escape the CFL, right? When you have this finite difference in time domain,
yes.
you don't have this. And the reason is that you have this implicit. It's as if you're solving implicitly, right? Because
in a sense,
you have this. Since your problem is elliptic, you have a global dependence on all points of the domain. So But Matt Zank is Matt Zank, right?
Yes,
The one.
gotcha.
Okay, and I remember that he was discussing that this could be a very good idea, but the problem is that you lose energy. So what did you plot the conservation of energy? What happens there?
Okay, so I did the plot like was it yesterday or 2 days ago to check for energy. You do lose energy in this case because of impedance boundary conditions.
Okay.
Because impedance boundary conditions basically are damping conditions.
But so impedance boundary condition are a Robin type of boundary.
Yes, Robin are for Helmholtz, and if you, in a sense, if you do the Fourier transform of Robin boundary conditions, you get impedance boundary conditions.
Okay, and then if you put a very small coefficient in front of the part of the Robin boundary condition that doesn't have the normal derivative, you should have conservation of energy, right?
Well, you approximate the fact that
you should have almost.
yes, in a sense, if you take the what is the boundary condition?
You're approximating
Okay.
a Dirichlet, right?
Yes, exactly. If you take theta and you let theta go to 0 or to infinity, you get either Dirichlet or non-boundary.
And did you try shifting that case energy?
No, because in that case, if you let theta goes to 0, well, if you put it to 0 or to infinity, of course, if you look at the what is it?
You have a dependence on
Yes, exactly. You have a dependence on theta, and then so everything breaks down. So it's no longer coercive in that case.
So
You
you
can. The thing is, this works for impedance boundary conditions.
And one last thing,
Yeah.
so you use a Hermite polynomial on Cartesian grid because you can
Yes.
do this tensor product. But I guess everything would work also with other C1 conforming elements like Iris and.
Yes. Okay. So it should. The only difficult. Okay. So what is it? Let me just find it. Okay. The only problem there would be that okay, in a Cartesian mesh, it's simpler because these are full gradients, and this is the reason why you need C1. Okay. You need full gradients, tangential and normal derivatives. Okay.
On the
If
armed
you-
edge.
Yes, on the boundary. Sorry. Yes.
On the D, yes. Okay.
Yes, and so with Cartesian mesh, well, it's easier to do it.
It's the coding. The
Yes,
problem
exactly.
there.
The coding is the hard part.
Okay, and
If you do it on a Cartesian mesh, it's easier. If you do like say on triangles, it becomes a mess. So
then this introduces the second question I want to ask.
Yeah.
Have you think about using something different from a conforming finite elements going to a conforming virtual elements in which you have this conformity for free?
we have not. We didn't. Well, okay, no. It's we didn't think about it.
Because there you have conformity for free, almost free. So.
Yeah. Okay, so we started from this because the idea was like, well, we are going through the trouble of doing this whole long calculation at this hugely complex bilinear form. We should use
But
conformity.
this calculation is at the continuous level, so you can
Yes.
still keep it, right? And then
Yeah.
you work with whatever discretization you try
Yes,
to put in
indeed.
there. So
Yes.
that's very interesting.
Okay, so I should take into account it, actually. Thank you.
Thank you. So is there any other question from the audience? Okay, if not, we thank again the speaker.